1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, that's better. Okay, dear ladies and gentlemen, that's the next morning, and I overestimated my how to say, skills of presenting the article, so it takes way more time than I thought. Also, I underestimated the size of the article, and it's 23 pages, but I haven't been ever streaming yet articles for 23 pages, so it takes really a lot of time. And right now in the morning I have approximately 2 hours to finish discussion of what happens there in the article, so let's just jump into the main topic and continue our previous discussion. And since yesterday I haven't opened this document and haven't thought about it, so let's just continue. I haven't improved anything, I just rest, and that's the next morning. So we have covered weak versus strong coupling, and a lot of comments are here that can help us understand what happens if we increase the strong coupling, but basically we have just several references, 38, 37, maybe 30, but I'm not sure about the 30, article 30, 39. So they will give us more understanding about what happens if we increase the strong coupling. Here, this is a collection of unclear and not so used statements, so that's hard. It's hard for me to comment how valuable are they, because, like, I mean, there are some predictions of energy gap, but Rossnagel could have drawn a plot about this energy gap, and it would be way more informative than writing large gap or small gap. Like, what is the criterion for large gap and for small gap? And other statements are not supported, not explained here. So that was the conclusion about this part. But right now we are coming to a similar part of comparison one dimension, two dimensions. And let's read what he writes. And again, this will be a similar paragraph of LaTeX sense that has a lot of statements which are not really explained. Okay, so here he starts with saying that there is this standard theory which is not really explained well here, but it assumes that if we have two-dimensional model, then this Fermi-surface nesting, which was mentioned in, is proposed for explanation of charge density wave. So that's an attempt how to get something approximately one-dimensional in two-dimensional model. And so in one dimensions we have the peak of susceptibility. I don't know what do we speak about non-interacting susceptibility. Maybe that's important, but like, I mean, susceptibility is the thing that is of course used, but I haven't yet saw that it's exactly non-interacting susceptibility. Maybe we mean that, yeah, maybe it's important adjective which tells us that then on top of this model of linear response that is assumed here, we need to also add electron-phonon interactions, and this way we can get the full susceptibility. But the theory that I was reading before about the susceptibility, it didn't tell me this. It was just, oh, there are these typical plots like hard function of susceptibility. So, but here it's written that dimensionality, yeah, so as I was trying to explain right now, so it affects this susceptibility, which will not have a peak Yeah, and it's written in the Gruner's book, which will be out, which will go discussion of which goes beyond of this stream. It also it's written that dimensionality has effect on flatness of Fermi-surface, and that's not the thing that I understand. No, because yeah, it's a complicated question. What affects Fermi-surface at all? Like here, it is actually an example of the Brilliant zone, which we have discussed, and that's before this modulation of Chernetsky wave. That's after the modulation. And that's a complicated question. What affects Fermi-surface? Here it's written that if we just increase a dimension, then it will change, which is obvious. But how exactly? It's not the question that I can answer. Okay, let's go next. Okay, so here that's a comment about in general the formalism that was done before, and unfortunately when I was studying it way before the stream, using another theory, there was a different derivation. I don't remember exactly this susceptibility there. Actually, I was showing you the derivation, and here. Okay, I have closed right now that book that I wanted to open. That's why there is no sense to open it again. But that's the theory of Green's functions, and they just calculate polarization operator, then they put it to normalization of basically the full Green's function of phonons, and that's how we can get their normalized frequency. So it goes without the susceptibility. However, maybe polarization operator is the susceptibility itself, or it's connected deeply to it, but that's the property that is not known for me. And in this sentence, we have just a comment about the theory that was presented before, that there is susceptibility, diverges, but it's also in the frequency so of phonons. So we get the finite temperature of the point where susceptibility, where frequency of phonons diverges. Okay, so here it's again the comment about what we have studied before. So that's this plot which is here. So that's the softening of the frequency. It means that it goes exactly to zero, and energy gain means that it's more energetically favorable to have this state with this gap. That's what we already know. Okay, and next sentence is the one that I don't fully understand. So so that's again a comment about the previous theory, but this comment requires deeper understanding of what it meant by this theory. And here, I guess that's the wave vector of singularity in the fallen mode, but we have this modulation of lattice and electrons, and they have also their own wave vector, and it's written that these wave vectors coincide, but so it's not clear for me why is it so. So okay, that refers us to the theory which is just cited, so if needed I will understand why exactly they coincide, but the theory that I was reading before wasn't pointing out this coincidence of these two quantities. But that's what is also well known in that typical theory of parallel instability, which is presented here. Okay, here there is a reference to some work where they where it's written, I mean, it's written here that in that paper it's written that it's not this instability is not stable against temperature and some other effects. So I don't know what is a lifetime broadening effect or momentum broadening effect. For me, they suggest some exotic effects which I haven't heard about, but okay, I don't know how to evaluate stability or robustness, which is maybe the synonym of stability. Yeah, so this analysis goes way beyond that standard theory, and also before we discuss stability, now we discuss robustness, and I was assuming that that's the same thing, but in order to understand at all what is written in the sentence, you need to read the cited paper. But maybe it means that some problems with other effects appear in this simple parallels model. Okay, but it's not clear if it's really important to take them into account or not. Okay, here it's the comment about the previous comment that that strange momentum broadening, which is not explained, is typical in quasi-one-dimensional systems in which there is the special buckling Fermi-surface. So, of course, it's not clear what is meant at all, but maybe the idea is that in some systems that's a typical effect which destroys to some extent this model. That's how I understand the statement, but anyway, that's just for the reference 13. It's written to go to that reference if you want. Okay, so here they, but that's actually a very expected statement that, like in this model, we have this, how to say, softening of the frequency. And theoretically, if we just do this model without anything else, we will have this frequency going to zero. But physically, of course, it would be very strange that this frequency will go exactly to zero because there will be other effects. And here these effects are named. And it was calculated that if you take into account these effects, then this jump is not that big. So if it before it was like it's written infinite, but hence it's not clear what is the infinite enhancement. Maybe it means some kind of inversion of this gap, but again, here it's written enhancement, so we need to think not about the phonon frequency, but about that plot that is not present at all in this article, but I was reading it about the Gruner's book. So that's the plot like goes like this of susceptibility, and yeah, that's Linhart formalism. So if you want, you can Google it. But I imagine what's going on here, and that's the plot of the susceptibility. Maybe we'll do the stream, one of the next streams about the Chernisty wave. So in typical linear response theory for one-dimensional case, it has infinite peak, and here if we take this effects into account, it will be a peak of just 5 times. Is it 5 times? Sorry, for 3, factor of about only 3 for this temperature and momentum broadening. And also energy broadening, but I don't know what these broadenings are. I need to read the cited paper. But okay, we understand general the statement. Okay, maybe the conclusion is that even though there are these effects, still this transition should occur. Okay, I wrote that it's not relevant, but actually it's like relevant because even though there are other effects, it still occurs. That's the main message here. Okay, Rossnagel asks us what is the role of Fermi-surface in this transition, and I don't know, it looks like a philosophical question. So in whole this formalism, it's very hard to point out the role of Fermi-surface, but maybe it will be written right below. Yeah, so here, okay, let me open it somewhere here. It's already approximately opened. I need to just a little bit scroll. So that's the formula that's assumed. And here he shows us that, look, if it's infinite and we want to be this quantity to be infinite because of unknown connection with divergence of high and the transition itself, and also divergence in renormalized frequency. I mean that it goes not to infinity but to 0, but still this special effect of the frequency. The link unfortunately is really missing because I don't understand if we have a finite susceptibility. Maybe we will still have like finite transition temperature to the state where frequency goes to 0. I don't know, I need to read the cited papers, but for now we assume that we really want it to be divergent or very big. So for it you need to have a small denominator and big numerator. And a lot of this k over which the sum is going. Okay, here it's written that we need to, like, the biggest contribution comes from the Fermi-surface, and I'm not sure why is it so, because looks that if we take any like, so we imagine that we have a phase space, and if we have a surface of equal energy and take the q which goes from one, I mean such q which will be also from one part of Fermi-surface to another part of Fermi-surface, oh no, not Fermi-surface but surface of the same energy, then it will still work, and psi of q will have divergence. But here is written that we don't need just surface of same energy, but we need a Fermi-surface. And why is it so? I don't know. Maybe it's obvious from this formula. Maybe Fermi function will play some role, but that's what's stated here. And now we have again a clear statement that in weak coupling we have the largest contribution to susceptibility near Fermi-surface, and I can't comment it because it's hard to trace how the coupling also affects this formula of susceptibility. But now we said that actually no, that's not the case, and effects from far states from Fermi-surface are not negligible. And okay, we need to go to the. Fortunately, I need to scroll. I don't like to scroll, but sometimes we need it. So it's written that this factor originates from from states way far from Fermi surface, and again that refers us to the paper 13 where these things are maybe discussed. But that's a very unclear statement. That's why it takes so much time for me to do the stream, because I think about a lot of unclear statements that go beyond the theory that was presented before, and which I wasn't working with before also. So that's a complicated formalism where everything is interconnected, and we have been speaking about susceptibility before, but right now we are speaking about the, how is it called? Delta E band, like change of energy gain maybe. Okay, I guess the energy gain was here. Yeah, okay, let's say change of energy. So susceptibility and something else gets give us the contribution to the change of energy of electrons, and totally the change of energy is because of also states way far away from Fermi surface. Why is it so? It's not written, but maybe this paper which gives us this value can explain it. It's paper 34, and here we have a paper 37, so that's not the same papers, but for some reason we so it's written here that, like, so it's the answer to this question about influence of Fermi surface, and first of all, it has the largest contribution to stability. Second of all, it has a big contribution to the change of energy, but that's not the one contribution, and another non-negligible contribution is from states away from Fermi surface. That's, I guess, the main message of this paragraph. And okay, and we again reference to this formula 20, and it's meant here that if we increase coupling, then Fermi surface will play a very little role in this, in the energy gaining, which is not, it's not written and explained. Why do we need to bother about it? And okay, maybe that's the connection of this Fermi surface with our analysis of the stability, because stability comes from energy conditions. So if we have way energetically favorable state, then it's way probable that system will go to it. And if we have unfavorable energetically state, then system will never go to it. And everywhere there is the Fermi surface assumed, so here it's written that it affects Xi and this energy that system this changed in the system if we, I guess, decrease temperature. I mean, no, we don't decrease. I mean, it's like about just comparison of energy, but then if we decrease temperature, then system should go from one state to another. It's also interesting, actually, like if we have a finite temperature, why we don't have even at finite temperature the divergence. Okay, it should be clear from what is written here, but it's a very good thing for practice. Okay. That's an interesting question to think about later, but right now that's the case, that only below the transition temperature we have the Chernetsky wave, and that's what we are told here, that there are two effects of Fermi-surface. Okay, now we have a next paragraph, which is a very unclear paragraph, and that's the only comments that I want to give about it, that K-space geometry is generally not favorable. What is meant by K-space geometry? Maybe it means that we have like Fermi surface in the brilliant zone and it has some special geometry, but I have no idea what is meant. So I was reading the sentence several times before the stream. I have read the sentence right now during the stream, and I still don't understand what happens in this statement. So for one-dimensional metal, for some reason, we have three-dimensional momenta space, which is very strange because we expect to have one-dimensional model with one-dimensional K-space. Maybe we mean that it's a quasi one-dimensional metal. And this Fermi-surface can coincide with discontinuities. So if we look at this K-space, there are some discontinuities somehow created, and they coincide with Fermi-surface. So maybe we should imagine this thing that was opened before. So that's the two-dimensional actually K-space or two-dimensional material, but maybe for three-dimensional case it's something similar, but three-dimensional. And if we have these discontinuities, then they coincide with some Chernetsky wave and other discontinuities. Okay, or this Fermi-surface coincides with discontinuities by Chernetsky wave. And it's unclear what is meant by these discontinuities. I will add later comments about it. Somehow these discontinuities are there, and this is linked to the already known effect that there is the gap at the Fermi surface. So sounds like abstract, useless comments, which are not understandable at all. I will write my comment about this later. So here it's written, I mean, that's the effect of dimensionality, and right now that's not the plot that we should look at because it will be further below in the article. We should look at that. Okay, let me just open it for this plot. And it's written about the next dimensions. So, okay, I already forgot what's here. This is just discussion of susceptibility. This discussion of effect of Fermi-surface. Now we have finally the discussion of dimensionality, which was announced in the title of this paragraph. So it's written that if you have two-dimensional metal, then Fermi-surface is not planar. So maybe when later we will see this plot, then we should look at it as approximation, because turns out somehow that Fermi-surface is not even planar, and that's something which I don't understand at all. We need also to have some formula for it, and I have no idea how to write any formula. Like for two-dimensional metal, I was always thinking that we have some Fermi-surface with some change somehow because of some, I even don't know what, but maybe a lattice configurations somehow. But I always thought that it's a planar, but here it's not planar, so it goes out of two-dimensional plane, which is of course expected for quasi two-dimensional systems, but we always model them just by 2 dimensions. I don't know why is it called so. And it's written that Boolean zone edges will only partially coincide with Fermi-surface, and how to explain it, I have really no idea. This okay, don't know if it's this a Boolean zone or little. I mean, that's extended maybe Boolean zone. But like I don't know how to explain this plot and why Boolean zone edges partially will coincide. Maybe it means about this plot. But like in typical case, actually, maybe the picture is like this, that we have this Brilliant zone, the Fermi surface is inside of the Brilliant zone, and they should not coincide, but here it's written only partially coincide. But what is the partially coincide? It's not clear. But these are two effects for two-dimensional bands, that Fermi surface for some reason is not planar, and it's not that easy as one dimensional, but we don't know what happens in one dimension. So like some statement about connection of Brilliant zone and Fermi surfaces here. And there is a partial gap. I was trying to understand what is a partial gap. I don't know. Maybe it means that for two-dimensional systems, only the upper band goes up and the lower band does not goes down. So we'll have not 2 delta, but just 1 delta. But again, we don't have any reasoning of this to be true. Maybe we need to read cited papers again. Sorry. Okay, maybe here it's written about general properties of two-dimensional metals, which can be different. But if we have, as I was saying before, some special Fermi surface that has a lot of features of one-dimensional system, then it will be like in this case, this parallel one-dimensional model will be more applicable, which is something that we have already discussed before. And it's written that it has some flat parallel sections, and okay, that's how this one-dimensionality can be realized. But everything here is about this formula, which I need to open this little scrolling. No, I was scrolling to the wrong side. So it's about this formula. So it's a good exercise to play with this formula and plot different dimensions and try to find out how into dimensions with some special Fermi-surface features this formula can give us bigger value of susceptibility. Yeah, so that's called the Fermi-surface nesting. The other thing is, like, as I was saying again, is about this formula. So this is the special way how to deal with this formula for two-dimensional systems. So here it's written that it can be used also for higher dimensions, but it's really unclear and no examples are presented here. So it's hard to see this statement which is done here, but so that's mechanism that is discussed a little bit here in one sentence. It's written that this mechanism can be also used for higher dimensions. So, but it's not again clear why and where. Okay. So here there are comments basically in this paragraph about general properties of two-dimensional materials, and also about this formula that we can still have divergence in some special materials, but later it will be written that this Fermi-surface nesting is not really working because of some reasons that are not always again explained, but still. So that's the proposed mechanism that we need to know in order to understand theoretical development of this theory. Okay, so here it's written, I mean, it was written before that there is this Fermi-surface nesting, and here it's written again that the effect of dimensionality is dramatic. So that's a continuation of the previous discussion, basically, that it's written that there is this Fermi-surface nesting, and before we have the logarithmic divergence, now we will have a not. And as far as I remember from the plot from Gruner's book, it's just like finite value of the susceptibility appears instead of the divergence. So here it's in a smooth peak, and that's exactly what typical linear response theory tells us. But it's also written that the position of this peak becomes dependent on Fermi-surface segments. And I don't know about position of this peak. It looks like a comment about advanced properties of the this formula for 2 dimensions. Like we select some special parts of Fermi surface which give us the biggest contribution to susceptibility, and yeah, like which parts we should select. It depends on the Fermi surfaces in general, and that's what's written here. So it's like very expected statement, but in terms of formulas, it's very unclear how to derive it. But luckily, we have a cited paper here. Okay, here it's written that we have another effect, which I don't know about at all, but it's written here that just this effect is here, and there are some nesting of saddle points in the band structure. So saddle point is maybe extreme of the band structure, like the lowest point of the band, or the like should be lowest point of the band, and some nesting of them can appear if these points are close to Fermi surface. So another effect can also be there for contribution to susceptibility. And if you want to know which, then you can go again to another cited paper. Okay, so here there is a little bit not clear statement again that they should have these materials that we are studying, but not only them. It's written about, in general, some layered chernecity wave materials. So they are known for weak peak rather than broad wave vector range. So weak, I thought it means by size, by height, and broad means by horizontal dimensions. And it's not clear why they write about the height and about the width in one sentence with the it's like, sorry, I misread it. Okay, that's the same thing. So it's not a contradiction. It's just a description of the peak. It's weak and it's broad. So sounds like exactly the thing that we expect from Fermi surface nesting. That in two-dimensional systems it will be weaker and broader. And it's written that somehow experiments confirm it. So it's a good idea to read these articles to understand how they confirm it. Okay, so here there is one obvious statement that here these Hahn anomalies, they are broader, and that's what we expect, that in reality it will be very hard to have this one-dimensional peak because we have a lot of two-dimensional materials, so there should be some little signatures of this softenings of phonon frequency, but yeah, so that's intuitive. but something like this should still be there. So to some little degree, this phonon frequency should be in some materials also like softened. And here there is another link of this to the electron-phonon coupling, but that's very unclear link, because one thing is to have the anomaly in the frequency of the phonons, which can originate from different things, from some special calculations, but they connect it, Rossnagel connects it to directly to the Horn anomaly, and maybe he knows a lot this theory, that's why he gave this statement, but it's not obvious that exactly these anomalies will give contribution to the value of electron-phonon coupling. I mean, that is very connected to the big electron-phonon coupling, but that's what we are told here. And I can't comment much the temperature dependence of susceptibility. It's written that it's weak, but I don't know the formula of susceptibility as a function of temperature. So I don't know much about this. Maybe it's meant that we don't have logarithmic divergences we had before, but we will have some little dependence of temperature. It's a good question how to use this formula, and maybe one can try to do it because temperature sits here in the Fermi function distribution. Oh, so if we master this calculation of susceptibility for two-dimensional systems, then we might derive this property, and that looks like a good exercise. But one need to really think about this formula and do the calculation and read some theoretical papers about the calculations in order to understand the statement. And another problem might be there, which we will run right now. Okay, so we again are reminded that actually the electron-phonon interaction should be k-dependent in general, and there is an isotropic Fermi-surface for two-dimensional systems. So I wasn't thinking about Fermi-surface and isotropic. I was actually thinking about it like this, because I know that that's the plot from the calculations. And Fermi-surface is very, very damaged comparing to just typical circle. It's very good. It's a very good exercise to derive such Fermi-surface from somewhere to check that indeed there is an understanding of what is the origin of such Fermi-surface. But that's what meant here, that that's anisotropic Fermi-surface, because if you go to this direction, you have this surface. If you go to this direction, you have this and this points of Fermi-surface. But why is it connected to the k-dependence of electron-phonon interaction? That's what I don't know, because I wasn't working with the models of electron-phonon interaction with momentum-dependent coupling. I need also to derive it from somewhere, and I haven't done it. So for me, it's a new approach for electron-phonon interactions, and they say that we really need it because Fermi-surface is anisotropic. But this connection is missing. And also they say that because of this k-dependence of electron-phonon interaction, the criteria which were discussed before are no longer valid. Okay, and we have this very expected formula for generalization of the susceptibility. However, let's just check. So here, I just noticed that we don't have a size 0 anymore. And okay, from this. Okay, I got a message from my friend. That's a good thing. Okay, so here what wonders me is that we don't have xi0, however, because that's how we take into account the interaction of electrons and phonons. Before we didn't have this interaction at all, then it's really unclear why this formula is so, because I expected that it will be like non-interaction susceptibility plus something with interactions. And here it's not the case. It's written that that's the purely different formula. Because like, look, if we don't have interactions of electrons and phonons, no, then we will not have parallel instability at all. Because everything somehow should originate only from this interaction. I'm just trying to figure out, so we have this formula and we have this formula, and this should be the limit of non-interacting limit of this formula. But if we set gamma to 0, then we will not get this formula. But this formula, yeah. So it's interesting here that this is a general formula, and it's not clear, like, if it's a general formula, why it plays such a big role for electron-phonon interactions. Okay, that's because of the formalism. I think it originates from this energy bands change, and then we somehow work with this energy, and that's why it's there. But the thing is that this formula has nothing which takes into account electron-phonon interactions, and we use it for the model of electron-phonon interaction. So that's maybe just the electronic part of the whole framework. Okay, that's how I understand it. And the question is that how to take non-interacting limit of this formula and okay, that's a good open question. Okay, let me write it to my list of questions. Let's write like this. Okay, that's the postponed question about this non-interacting limit. I don't understand it. But that's the statement that if we have a k-dependent interaction between electrons and phonons, then that's the formula which we should look at. And that's not connected at all with this formula, because they're very different, right? They have different physical meaning. Different meaning in general. That's for interacting electronic system. That's for non-interacting, and that's what is written here. And okay, to remind you, here we have somewhere the Hamiltonian. Oh yeah, that's the Hamiltonian. So here we have this term that couples electrons and phonons. So here we will have a more general coupling between them. It's also interesting that here there are not only two indices but also a prime, and this prime means that that's like this object should have two indices. That's maybe just notation. Okay, now we have maybe important citations for our understanding of the matrix element. So when is it large? When they have large and opposite band velocities. What is it band? That's not what I know. But okay, we can understand at least the statement that of course we assume that there is an energy band of electrons and of phonons. And I think we assume that there is only one band for electrons and phonons, because band is not taken into account. But band is the energy of as a function of q, and we can calculate the velocity of this exactly position in the energy band on the q on the k-axis. And if velocity is large, then this coupling is large. And I don't know how to explain it. Oof. There is this theory that is mentioned here actually that that formula originates from the potential that is created by displacements of lattice. And maybe if we have like higher velocity, then there will be higher displacement, and that will give a bigger potential to electrons. But I don't know why is it so. It's really interesting to read this paper once about this k-dependent coupling and what is the origin of it and why it can be bigger for bigger velocities of the band. Maybe later I'll do it. Here we are told that that's the case not only for two-dimensional systems in general, but also for layered density wave materials. But okay, if we look at this formula, then maybe this dependence on k will not give still the big contribution, because we have other terms in the sum, and I mean other parts of each value under the sum, and this another part will contribute more than this electron-phonon matrix element. I mean, dependence on the q will be not the big as the contribution of this part of the term under the sum. Why is it so? Of course, it's not explained, but there are again citations. Okay, and there is just grammatically not so clear from your statement that peaking are more pronounced but not sharp enough. What is it meant? It's very not clear. We can't understand it, but there are cited papers. In general, the conclusion that there will be still peaking, and maybe these peaks are not that sharp that were in one-dimensional case. It's also not clear this psi 0 of q. I'm just confused that why do we have a vector here like this bold symbol if we deal with one-dimensional system. Let's just double check this. That's the first time I ever think about this property. Okay, you see, like even after doing the stream and during the stream, I didn't notice that. Why do we have the vectors here? Maybe because we consider these formulas as general formulas for different dimensions, but then as we have seen here, what's written. And then we use it for one-dimensional system. Yeah, it's a good question. So here everything is written about one-dimensional system, and then will be generalized for two-dimensional systems. But but let me just check one thing. Yeah. Okay, maybe, but I mean, yeah, but here it's written that it's not actually the correct statement, because for two-dimensional systems, this should be the formula, because of this unexplained reason of anisotropicity. So yeah, okay, I will add to my comment. Okay, maybe we are told that like you see, like if we go from one dimensions to two dimensions, I mean, it's also not clear that like here it's like susceptibility of interacting systems, so it's a full susceptibility. Before we were given a non-interacting susceptibility, so just trying to connect what's written here and this formula to the previous theory that we have discussed. And speaking of zero, I wasn't thinking that deep about this statement before. Not sharp. Okay, let's just skip this question about dimensionality, because as you can see, it's written very unclear. There are a lot of parameters that appear here. Like we don't even have some quantities that we compare. We had xi0, and the whole formalism that assumes something that is not written there explicitly. And here we have the xi and the and then we are discussing, but like that's a bad theory here. That's why I was thinking more than I expected, because we compared two different quantities. Xi0 is for what? If it's for one-dimensional system, then okay, we shouldn't consider it as a one-dimensional system, because Q is a bold Q. It should be also for two-dimensional systems. So if we take a non-interacting limit, then we'll have a not sharp peak. Okay, so my version of what's going on is the following: that we had this non-interacting susceptibility. It's yeah, it's a general formula which plays a role in the formalism, for example, for one-dimensional systems. Then we have this idea of Fermi-surface nesting, and using this idea, we can calculate the non-interacting susceptibility for two-dimensional systems. That's useless quantity, because actually we have the change of Fermi-surface, and we need to calculate different value. So here it's not clear if we have taken into account the change of Fermi-surface, but common sense tells us that we should take this into account. But also if we take into account interactions, then there will be this term in this formula. And now we can compare the interacting susceptibility and non-interacting susceptibility. Non-interacting susceptibility should have a peak, but not a big one. Maybe here it should be something written about yeah, so the finite enhancement. So here we discuss this non-interacting susceptibility for finite enhancement. Oh, for two-dimensional case where it's written that there will be a finite enhancement. Now we are working with also the interacting susceptibility for this case. We have a very different formula. It's not the previous formula plus something, it's just a purely new formula. And it's written here that this formula will have also a peak, but and the peak will be bigger than for non-interacting case, but not very sharp still. Okay, we have these references to figure out what's going on. Maybe we need just 48, 23, and 23 to figure out what is meant. I don't know. And that's the idea. So if we do susceptibility, I mean, that, yeah, actually, like, okay, somewhere there for non-interacting model. Okay, can it be like, it's actually a good question, like, can it be that we have a Fermi-surface non-isotropic, but because these two different parameters, and I'm a little bit confused because here it's written that for two-dimensional systems we have anisotropic Fermi-surface, and then they speak about, Rossnagel writes about the interacting case, and he connects these two dimensions with the with existence of coupling of electrons and phonons, but that's a very unclear explanation because by default we should have two dimensions with, as it's written here, an isotropic Fermi-surface, and in this case we will have the psi0, we will not have psi. Psi is for interactions of electrons and phonons, and it's not clear if we assume, like, I mean, just not clear, it's written very not clear. We can't understand if in two dimensions we should take into account an isotropic Fermi-surface or not, because from one side it's written that it gives us this formula with decoupling. From another side, it's written that for two-dimensional systems we have this little enhancement of susceptibility. So maybe we should consider this theory here is absolutely wrong theory, because here it's explained that actually if you have two-dimensional systems you should start with an isotropic Fermi-surface, and here it was just a formula for the like the one-dimensional form, I mean the general formula, which, yeah, which doesn't take into account anisotropicity of Fermi-surface. So looks like these are useless calculations because they use just their own formula. Because it's explained right in like 3 paragraphs below that actually we have the anisotropic Fermi-surface, and here it's not taken into account, so you're calculating the useless quantity. But here, if we take into account the isotropicity of Fermi-surface, we are also getting the coupling of electrons and phonons, and that's also very much not clear because these are two different phenomena. So you should distinguish like non-interacting electronic systems with an isotropic Fermi-surface And what should we write for this? Should we write this formula or should we write this formula? None of them applicable, because here it's for isotropic Fermi surface, and here it's for electron-phonon coupling system. And that's the case. That's what's written here. We know more. We know cited papers. Maybe we can read them and understand it better than it's written here. And okay, another unclear statement, because it's not clear what are we coming to and how. Maybe we are assumed to use the same formalism, and in that formalism there was somewhere assumed Fermi-surface, and we have discussed it, the role of Fermi-surface, that somewhere there it's present for the change of energy and for susceptibility, but we have different formulas, and electron susceptibility and Fermi-surface does not have such a big influence. However, like, it's not really clear why these parameters are really important. In criteria, they are present in criteria of here, for example, in this criterion of parallel susceptibility, there is this xi0, and here the normalization of frequency there is xi0, but that's an abstract statement which is not clear at all what really is meant by role is diminished. Here we have the formula, so what will be with this formula? We don't know. We need to read cited papers in order to understand what is meant. But in general, somehow some modifications can be made and some effects should arise. For example, effect of the anisotropic coupling and something else that I have approximately forgot already. But this Fermi-surface nesting is the way how to work with this formula of susceptibility. For the two-dimensional case, however, maybe it's not really working. I like that I have passed through all this text, so I'll revise it for myself later, but I don't want to again return to it right now. It's a collection of really unclear statements and references. Of course, there's a big value in them, because without the statements and references I would not understand myself anything, but even them are not enough to understand at all what's going on and why. And we have a nice table which is approximately useless, but it summarizes everything what we have discussed. Okay, maybe not everything. It's written that there is cylindrical geometry of Fermi surface, and when I read this, I just imagine like this and try to this image and try to discuss this all what's written here. There's a two-dimensional case which will be calculated anyway. So I don't know why we at all have this discussion, because it looks like a very useless discussion. He will later say, hey, I have t-dividing models that give me these results. So I think it looks like he was reading, like 6 papers, and then he was thinking for a week, okay, how to write this 1 dimensions versus 2 dimensions, and okay, let's make several comments and summarize what happened in several papers. That's how it looks like. Okay, it's a good thing, but it's not really informative. And also, we don't know how to use the models which are proposed, and even for 2 dimensions, exactly for 2 dimensions, we are told that there are other effects that go beyond the previously discussed model. So we need to re-understand the previous model from the beginning in order to work with 2 dimensions. So I don't think that's really a high-quality theory. It gives good references, and that's the main value of this paragraph. And right now we're coming to the second paragraph, and I have approximately half an hour. So we will discuss like excitonic insulator instability, and that's definitely more than, I mean, I definitely will not have time right now for this stream to discuss something more. Okay. Yeah, that's just a comment which I wrote here, that this theory assumes that if we add electron-phonon interactions, then we'll get a transition of phase transition and structural phase transition, I mean, but that's not what I see right now. We just have the formalism. It's the question which I wrote about this formalism. So if you look at this formalism, then what happens? We have change of the lattice and energy and the electronic energy, then some criterion, then we get the non-interacting susceptibility when we plug that functions. So I just don't understand at which point we insert, I mean, something which has exactly electron-phonon interactions. So suddenly the frequency becomes renormalized with this parameter G, and I don't understand why. Okay, it's a good question actually. I didn't think about it before. Okay, that's a good question. So that's what I wasn't understanding here, that we don't have a theory that we have like free electrons, free phonons, and now we couple them and we get the stability. I mean, we maybe have that, definitely we have it in the world of science, but in this article we are presented with just K formulas which do not explain how we can add the coupling and get some phase transition. But okay, that's the theory that we have right now. And now we are generalizing this theory to two bands with small direct band gap. And I don't know what is the small direct band gap, so I can't answer. But some band gap. I was studying Kittel, by the way, solid state physics, but right now I don't remember and I haven't reached that part of learning what is the indirect band gap. So in this case, if there are two bands, then electrons from different bands interact, and because of this electron-electron interaction, there can be a excitonic insulator instability. And that's the topic that is here discussed and which we are going to go through. And my understanding was that like the generalization goes to the direction of many bands. And if we have many bands, then we have interaction between them. So it should be an extra effect on top of the effects that are discussed. But as far as I remember, it will be here there will be different statements. So let's just go further and understand what Rossnagel wrote. Okay, so we parameterize these bands as these functions. So we find the energy gap and we have a parabolic dispersions because we are interested in just one region between these two bands. And also it's not clear here why do we have a transition between like semiconductor and semi-metal, because I would expect transition to a metal, and semiconductor means maybe that there is a gap, but it's a little gap. I mean, we have here exactly explicit definitions. If e.g. bigger than 0, that's semiconductor. If it's less than 0, then it's semi-metal. But it's not really clear why we have such definitions. But that's the clear formulas with notation. We just to remember that for the lower band we have at 0 energy, and upper band is shifted by Q0. I mean, that's just notation. We can, I guess, define it differently, but that's a convenient notation. It could be vice versa. It could be k minus Q0 here and k just squared here. But okay, we can start with this parameterization of bands. I'm just a little bit confused because later it will be written that it will be hard to distinguish that if we have an excitonic insulator or the Chernetsky wave, the gap, or excitonic insulator gap. So maybe what I was saying here, that this is another effect on top of the previous effect. Maybe that's not the case. Maybe that's a purely different mechanism of formation of Chernetsky wave. So that's the two options what could happen, and we'll discuss further what happens. So we have here an illustration which shows us exactly like the gaps, the bands that were before, that we have just seen in this formula. So these dashed lines are the bands of the electrons, and this is for yeah, I don't know how we can call them electrons or holes, but these are conducting electrons, these are the valence electrons, and this is the energy gap. So we have covered these dashed lines. So here it's written that after this like new phase that will be discussed soon, we will have these red lines, and as usual thickness denotes spectral weight. I wasn't explaining what is a spectral weight, but maybe it's number of states that are allowed to have this energy. But I need to work more with spectral weight in order to deeply understand it. And it's written here that band gap has become smaller than binding energy, but here it's not really the case. The binding energy is this one, and the gap is still this one. So I don't agree with the statement based on this picture that it became smaller. But these are two phases. So in the second phase, there is this different, the energy bands are changed, and there are new energy bands. I don't know how to explain why they appear. That's strange that they appear, but that's what we are told. And as before, that was the phonon frequency. There are optical phonons and acoustical phonons as usual in the Bayes or Einstein's model. And what's written here? Okay, so here we have still how to say, divergence, or like, I mean, singularity of the frequency, that it goes still to zero, approximately to zero, maybe by purely different mechanism, which is called the excitonic insulator instability. And these are the change of the phonon modes. It's written also that here there is a strong interaction of this exciton mode with the phonon mode. Okay, maybe here it's the exciton modes, it's not the optical phonons, and these are exciton dispersions. So exciton, I guess, is just electron which interacts with the hole. So basically we have two electrons interacting one with another, and because hole is equivalent description of some electronic phenomena, so in general that's the special electron which combined of approximately roughly saying two electrons. So I don't know why we had the horizontal dispersion of the exciton if it doesn't interact, but that's what is shown here, that originally we had the horizontal line and we have interaction of electrons and phonons. That's why both lines are normalized or are changed, and they're changed only in this region. Here in this region, these are not changed at all. And that's the quantitative picture of this phenomenon of excitonic insulators. So maybe indeed that's like a parallel phenomenon, but then it's interesting. Okay, I will write this question myself, so here to myself for later. If okay, I will answer this question myself, because it seems that channelized wave plus two different bands are not the excitonic insulator physics. But let's check. So we have 1 page, 2 page and a half. So definitely will not go through it. I will just finish this page and it will be already better than nothing, and we will continue next time with finishing excitonic insulators. So it takes really a lot of time on this article. So here we have a description of this plot, which I'll better open here. Where is it? Here. I need to, yeah, excitonic insulator. Just click this nice button of opening PDFs, and it's arranged a little bit not in the place where it should be, but it doesn't matter. Yeah, so let's see. Let's keep this image always near us and continue reading. So I guess we meant that we start somewhere here, so we already have EB. So maybe we are assumed to already have this change, like the binding energy. So some physics is assumed if we have these two bands, and because of this physics, we have already this EB shift to the lower part. Okay, so here we are not told what we are changing. I'm trying to understand. Maybe we are changing the energy gap. So what if we are decreasing this energy gap, then we will have appearance of binding energy, this EB. And if you, of course, decrease the energy gap, then at one point they will go to zero, the difference between them. So this will increase, this will decrease, and of course at one point it will go to zero. I'm not sure that it's possible to just tune such gaps artificially with some light or something else, but I guess that's what meant here. Reduce, yeah, that's what's written here, that's what I missed. Indeed, as I thought, we reduce this gap somehow, and then this little feature appears, and then it grows, and once this binding energy becomes as big as the gap. And later, some spontaneous formation of excitons occur. That's just a reference to some assumed formula in physics, which is not written here. Okay, I'm trying to understand this sentence, which unfortunately has no comments from me because maybe I didn't read it very carefully, as careful as previous sentences. So if we have a little band gap, then what? Exciton energy of a plasmon can go to 0. Comes. Okay, so some excitation energy can go to 0. And excitation energy, it's not written here what is the excitation energy. We have binding energy, we have gap, so let's imagine a new parameter, excitation energy, and this parameter will go to 0 if we start with little band gap. Yeah. Band overlap becomes smaller. What is the band overlap? So I don't know. I thought it could be like big overlap. If bands overlap big, then I don't know. I don't know how to understand the statement. There is a new parameter. There is some band overlap, which is not explained before. Maybe if we decrease this gap for this. And we start from little values of the gap, then exciton, the special energy of these effective particles so this energy will be 0, which is very not informative. We don't know what's going on. We don't know how is it connected to the previous statement, but let's how understand this sentence. And so this special state occurs, and we are linked to some assumed theory that it can be explained by screening effects. Of course, we know that there is a chapter in Kitter's book about excitons, but okay, maybe I indeed need to prepare myself during 3 days in order to understand better what's written here. But it's linked that this effect of appearance of the gap and this announced change can be explained by a screening theory. Okay, maybe that's an important next sentence, that insulator appears. So if we decrease band gap, we assume that maybe this should be a metal, because bands should be close one to another, but it's not the case because there is a Coulomb attraction. Yeah, and we should have a number, like small number of electrons and holes. Why do we need to have a small number of electrons and holes? That's what I don't know. Maybe because of this quasi-particle picture to be applicable. But I always think about everything in terms of formulas, and I don't have formula on top of my head. about the statement. So that's a clear statement for me. But maybe idea is that yes, like the electrons and holes will be attracted. Okay, there will be some screening. No, let's check. Sufficient screen. It's so unclear. So if we have electrons in the hole, they're attracted because they have different charge. Then yeah, there will be screening, but it will be not a big screening because of some reasons which are not explained, but that's the clear statement that screening will not help to reduce attraction of electrons and holes. And bound states are formed, and because of this attraction, bound states are formed, so there will be no movement. So that's a very abstract explanation, which is not connected to formula at this stage. Maybe later, maybe in the cited papers, this is connected, but right now, that's the intuitive explanation of what's going on. And that's what only I know. Some physics is assumed, which is not written here. Normal insulating and semi-metallic ground states are unstable. So if we, I guess, I thought bond energy is changing. So if we change the ground state such that I need to move camera like this. Yeah. So so if we decrease the energy Eg such that band energy appears and such that this equality is satisfied, then we have this instability. Which instability, it's not clear, but maybe it meant that there is this insulator that is formed. So sounds like there is a big theory behind these statements, but okay. Okay, let's just finish this. That's a new paragraph already, and that's a big paragraph. Okay, we'll just start this big paragraph, but we need to finish at least this page. Okay, here it's written what I was mentioning, that with this purely different ideas, so maybe with purely different models, which and will be actually a formula here, which is not really explained much, but I will comment it later. So it's written that with this instability, density wave appears and lattice distortion appears. So that's introduction to the future discussion of how to distinguish if we have an excitonic insulator or a charge density wave. So they say here that another like density wave indeed appears in scope of this model, which is not explained much, but we're given the main statements about this model. And the last statement that I will discuss today is that there is also a spin, but we are not discussing spin. However, if you take into account spin in a clever way, you can get a special antiferromagnetic spin density wave, which is not something that I know, but there is this model. Maybe there are some confirmations of these effects. So it's really interesting actually to figure out what happens in these experiments and figure out which theory is applicable and not, or which theory is not applicable. So that's like my PhD, that's why I'm doing it. So we have covered this introduction to excitonic insulators. We have covered the dependence on dimensionality, and totally we have covered 1 page, 2 pages, 3 pages, and 4 pages during this stream. Like this, and yeah, that's me. So thank you very much for attention. I hope I will do another stream today because I really want to finish at least half of this article. I really underestimated how big this article is. And also, as you see, a lot of statements are not as clear as I want them to be. This is just referenced. We have a lot of references, citations, and some statements are a little bit contradictory. But I'm not expert in this field, so after several streams I will understand much more. And another goal that I try to achieve is to show that that's a really easy and comfortable framework to work. This focus structure tool, you can easily write comments, present your findings, get some new papers. You can download them, insert PDFs, extract to LaTeX. That's a very comfortable framework. That's why I just take advantage of it. I really like what it gives me, and I hope that this project will grow. So I will continue today in the evening my streaming. Bye bye.